Okay, so let's see one question based on the Mealy machine. Here we will see the numerical of for detecting the sequence pattern 0101, and that is not overlapping. This time we will see overlapping. So this numerical is based on detecting the 0101 in case of overlapping. So here this question again start with a state diagram. So first we will try to draw the state diagram. As you know, the state diagram for the Mealy machine will start with a state A. So here I am drawing state A. When I receive the first bit correct, that is 0, I will go move to the state B, and my output, this is output, will be 0. Why? Because we have not received the correct pattern till now. After B, if I will receive 1, that is my second bit correct, then I will move to the another state C, and output is 0. After C, if I will receive the third bit correct, that is 0, by 0, I will move to the D state. After this, we have to check whether it's a overlapping and non-overlapping. As this question is based on overlapping, we have to check how many bits can be in overlap. Now here I can consider certain input pattern 0 1 0 1 0 1 like this. So I will receive 2-bit in overlapping. There is a possibility of 2-bit in overlap, right? You can see this 0 1 and this 0 1, these 2 bits are in overlap. So if there are 2-bit in overlap, you have to skip the 2 state from the beginning. 1 state, 2 state. You skip these 2 state, and from D you move to the state C. Once again, I am repeating, you have to check how many bits are in overlap. If there is 2-bit in overlap, you have to skip 2 states. If there is a single bit overlap, you have to skip 1 state from the beginning. And if there is 3-bit in the overlap, then you have to skip 3 states from the beginning. So here, as we are having only 2-bit in overlap, we are skipping 2 states. Okay. And what we have to write down here, 1 by 1. This is the correct pattern. Now we have to check for the non correct bit input bits also. So for example, you are in the state A. We already checked if you get 0, you will move to the state B. But what will happen if you get 1 continuously? If you're getting 1 continuously, that means we have not received a single bit correct because my first input is 0. So here I will move to the same state and I am writing 1 by 0. Now I'm just changing the color, 1 minute. Now if we are in the state B, that means we have a single bit correct, that is 0, and I was waiting for 1. If I will get 1, I will move to the state C. But if you are getting 0, in this case also we have a single bit correct, right? Because we after 0 we require 1 0 1, and in that case my pattern will be completed, right? So here if you are getting continuous 0 also, we have a single bit correct, and the single bit correct state is B. So here I am writing 1 by 0 by 1, 0 by 0, right? Why? Because 0 is the input, and as we have not received the correct bit pattern, so your output is 0. Now if you are in the state C, we already have 2-bit correct, that is 0 1. I was waiting for 0. If I will get 0, I will move to the D state. But what will happen if you get 1 here? If I will get 1 here, my complete pattern will be lost because I was waiting for 0 1 0 1 pattern, and after this I require 4 bits. 4-bit means all are actually required. Okay, we don't have a single bit correct also, so you have to start from the beginning, that is A here, and you will write down 1 by 0. Now if we are in the state D, that means we already have 3-bit correct, that is 0 1 0. I was waiting for 1. If I will get 1, I will my pattern will be uh, received correctly. But what will happen if I will get 0 here? If I will get 0 here, I have at least single bit correct, because after that I require only 1 0 1. Right? So at least one single bit is in the correct. That means single bit correct state is B. So I will move to the B state, and I will write down 0 by 0. Always remember A is the 0-bit correct state, B means a single bit correct state, C means a 2-bit correct state, and D means a 3-bit correct state. So now we have this state diagram. Now we have to draw the state table by using this state diagram. So here I am drawing the state table. In the state table, we have present state, then we have input, then we have next state, then we have output that is represented by Z, input is represented by X. So first we have to find out that many things, and then we will go for the which type of flip-flop we have to use. Okay, so how many states are there? 4 states. So I'm making 4 lines here. 1, 2, 3, and 4. Here I'm taking A. Why? Because in A there is a possibilities of 0 and both type of input. Now B, either input is 0 or 1. For C also input can be 0 or 1. Similarly for D also its input can be 0 and 1. As we have 4 different, okay, now after that we have to find out the next state. If you're in a state A and you are getting 0, that means I will remain in the same state A. Sorry. If you are in A, you will move to the B state, yes. If you are in state A and you are getting 0, you have to move to the B state. If you are in the state A and you are getting 1, you have to remain in the same state A. If you are in state B and you are getting 0, so 0 means same state B. If you're in state B and you're getting 1 as an input, you have to move to the C state, that is C here. Similarly, if you're in state C and you are getting 0, so you have to move to the D state. If you're in a state C and you are getting 1, so you have to move to the A state, that is A here. If you're in state D and you are getting 1, D to 1 C and D to 0 is B. So now we already received the present and next state. But as you know that in digital system design or machine, we cannot represent any alphabets. It should be in the binary form. That's why we are considering the binary of A as 0, 0, 0. Why we are considering 2 bits? Because we have 4 states. And by using the 2-bit, we can represent 4 states. A will be represented by 0, 0, B will be represented by 0, 1, C will be represented by 1, 0, and D will be represented by 1, 1. As I am representing A as 0, 0, right? So 0, 0. B is represented by 0, 1. This is 0, 1. This is also 0, 1. C is represented by 1, 0. This is 1, 0, and this is 1, 0. D is represented by 1, 1. So this is the next state, and output is 1 only when you are moving from D to C. So D to C, we have the output 1. For all other condition, it is 0 only. So I will write down zeros. So this is the state table. After that, we have to decide which flip-flop we are going to use. For example, we are using the D flip-flop only. So now, as we are using 2 bits for the representation, we will get D2 and D1 at the output. Assume this is Q2, this is Q1, and the next state will be represented by Q2 plus 1, and this is Q1 plus 1. Now, as we are using the D flip-flop, we require the excitation table of D flip-flop for writing in the state table. So Q2, this is Q1, this is Q1 plus 1, and I'm writing the excitation table of D flip-flop. Excitation table of D flip-flop. So this is 0, 0, 1, 1, 0, 1, 0, 1. So this will be 0, 1, 0, 1. Here the important point, the value of D will be similar to that of Qn plus 1. That means if you are writing the equation or answer for D2, it is similar to that of Q2 plus 1. So you can write down 0, 0, 0, 1, 1, 0, 0, 1. Similarly, D1 will be similar to that of Qn plus 1. That is 1, 0, 1, 0, 1, 0, 1, 0. Now after this, we have to find out the expression for D2 and D1 by using the K-map. So here I am drawing the K-map. So this is the third step where we are finding the expression for D2 by using the K-map. And as we are having the three inputs, that is Q2, Q1, and X, we are having the three variable K map 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Why we are writing like this? Because in the K map, we write down the gray code. Okay, we design the K map by using the gray code. D2 is 1 here, that means it is 0, 1, 1. Okay, 0, 1, 1. So here we have, here we have, here we have, right? So now we will make the group here. This is one group, another is the single expression, and you will get the value of D1 is equals to Q naught X plus, sorry, Q1X, Q1X, Q2, Q1 bar, X bar. This is the expression for D2. Similarly, we have to draw the K map for D1. Here also, this side I am taking Q2, this is Q1 and Q0. This is 0, 1. Here it is 0, 0, 0, 1, 1, 0, and 1, 1, and 1, 0. Now we will see wherever your D1 is 1. So 0, then 2, then 4, then 6. Okay, so you will get the expression here. This is 0, 2, 4, and 6. So that will make a quad, and for this quad, the expression of D1 will be equals to X bar. Similarly, we can find out the expression of Z. Z is 1 only one time. Z is 1 only one time whenever this is Q2 is 1, Q1 is 1, and X is 1. That means Q2, Q1, and X. So this is Q2, Q1, and X. Now we have all the expressions. We have to draw the circuit diagram here. So here you see, I will draw the D flip-flop here, and I will say this is D2 and this is D1. If it is D2 and this is D1, the expression of D2 that we calculated is having two expressions, min terms. Along with that, we have one OR gate, and that is connected as a D2. So here that value you have to connect is, this is Q1, this is X, this is Q2, this is Q1 bar, this is X. Similarly, this is X bar. Along with that, we have to give the same clock to all the flip-flops. And from here, you will get the Q2, and from here, you will get the Q1. And that value you need to connect to one AND gate like this. And here you have to connect the value of X, and this will be the Z. So this is the complete diagram. Along with this, you can also draw Q2 bar and Q1 bar. So this is the Mealy machine for value 0, 1, 0, 1 for overlapping.